Evening participants. The topic for current session is application of DSC analyzer and confocal Raman spectroscopy in research and development activities. Our keynote speaker for this current session has joined us. Now I would introduce him to all the participants. The keynote speaker for current session is Dr. Rajkumar Arya. He is currently working as an associate professor in the Department of Chemical Engineering, Dr. B.R. Ambedkar National Institute of Technology, Jalandhar. Dr. Arya has attained his PhD in Chemical Engineering from IIT Bombay, his Masters in Technology in Chemical Engineering from IIT Delhi, and Bachelors of Engineering from HBTI, Kanpur. As per his other positions, he has also worked as an associate professor in Thapar University, Patiala, and has also worked in JP University of Engineering and Technology, Madhya Pradesh. Currently, he is working on a project funded by Sarab DST worth 42 lakhs. He is also an expert of Research Proposal Committee, Council of Science and Technology, Uttar Pradesh. He has received many awards. Amongst them, few are, he has received Best Undergraduate Research Paper for publishing in Highest Impact Factor Journal. He has also been granted third position in poster presentation during CamCon 2016. The list of his laurels can go on and on. He has guided several PhD, Masters, and MSc students. He has also been the keynote speaker on many invited talks. He has published more than 50 articles in many journals of high repute. He has also attended various conferences in India and abroad. His areas of research and expertise are polymers, polymeric coatings, nanoparticles, and Raman spectroscopy. We welcome such an dignitary in amongst us, and we would request him to kindly present us with his expertise. Thank you, sir.
Thank you very much, Dr. Bhavna, for such a nice introductions, and very good afternoon to all organizers and participants for this program. I think this would be the second session of the day.
Yes, sir. For today, it's the second.
So yeah, so we will start our talk from that DSC analysis. So I am thinking if the organizer permits, so I am thinking that way. So let me give the demonstration first and followed by theoretical explanation if you permit. Otherwise, I will go explanation first and then demonstration part later. What do you suggest?
Sir, as you feel convenient, sir, it's all right.
Okay, so it's actually afternoon, so many of us tired, had lunch and something, so I don't want to make them sleepy. So let's have visual demonstration part first, and then I will explain the theoretical concept behind that. So actually here I will explain that how would you actually load the sample, how would you prepare the sample, because that is the most important part a student or any of the researchers need to do, because you should know everything from by your own if something is getting wrong. So you should be in the position to identify what is getting wrong. You cannot completely dependent on the lab attendant or technicians in that way. So you should be also vigilant during that sample preparation and loading, because that will completely means if the sample preparation and the loading is not proper, you would be wonder that what type of data you got, and you have prepared sample very well in laboratory part. You did everything full care. Now you are not getting the result as expected by you or the supervisors. So in that case, there could be nothing wrong with your sample. Actually, it might be something wrong during the analysis process. So it is most important to the researchers to be present while the analysis is being done. So let's see this demo part first.
So in this lab, we have a thermal analysis facility
And for that we have the DSC analyzer supplied by Saturn France. So this analyzers can give you the data from sub-ambient to up to the 700 degrees Celsius. Sub-ambient means from minus 70 degrees Celsius, and to maintain such a low temperature we have this cryo chiller. So this can bring down your sample temperature up to minus 70 degrees Celsius, and if you want the temperature lower than that, then you can have liquid nitrogen facility which can also be attached to the same equipment. So the first part is that we have to prepare the sample, and to prepare the sample, this is the crucible. So crucible, you are not supposed to touch it, so practically you have to use the tweezer for that and take out one particular crucible. So let's say this is of 120 microliter the volume. So first you have to weigh the crucible and make sure that you have a semi-analytical weighing balance, means at least 0.1 mg. So once you weigh the empty pen, so after that you can note down what is the empty weight of the pen, and then probably you can tear it, and then after you have to put your sample. So sample should be in such a way that this complete alumina crucible need to be filled from the bottom side, so that you should have a perfect contact that your sample is touching entire bottom. So you have to fill that amount, and maybe you can recheck it, your weights, what is correct, or have you teared it properly or not. If not, you can re-tear it actually. So you can see that it was perfect tear. Now you have to put the sample in there. So for time being, for this demonstration purpose, we are taking a sample of polycaprolactone. So you can see that sample size is some polymers are big, some is the smaller one. So sometimes you need to cut the sample actually. So let's say we have these two samples, and out of that we need somehow 40 milligram. For this system we need 40 milligram of the minimum weight in order to completely cover your bottom of this crucible. So you have to charge it here and put it inside that. So you see that this quantity is 60 milligram, so slightly higher than 40. So either we can decrease this quantity or break the sample. So cut the hole. So since the sample size was bigger, so we have somehow cut it down with the help of the knife. Now we can pour this quantity, maybe this particular sample there. So if you can re-tear it if somehow it fluctuates. So if you pour it here, so you can see the sample quantity is 53 milligram or something, 54. So we can go ahead there. The reason about this, this actually crucible is very big in the size. Actually this is something 120 microliter, so you can have such a large quantity also as well. So once it is prepared here, now the next part is that you have to cover this particular crucible. So for that we have a crucible lid, and there you can cover it with the help of this crucible lid and put it here. And this is actually you have one is cramping tool. So here you can take this and put this entire crucible here, this one, and so this is for a smaller quantity actually. So this is for the smaller quantity, 30 microliters. So this side is for 120 microliters. So you can find the difference. This is now fully covered. Now on top of that, just put this lid, and this is the clamping tool. So you put it here on top and just press it hard. So this way you are just locking it. So this way now your sample is ready. So this you can say now your sample is fully tight here. So nothing is, this would make sure that while you are heating the sample, so sample will not spill over the furnace or the sensor. So next part is that we will show you how to mount it in the DSC analyzer. We want to mount the sample. So this is the part of the furnace you have, so you have to take it out carefully, and this is the covering, so you have to remove this again carefully. And now you can see from here, these are the sensors. You can see that one sensor is this side, another is this side, another. So there are 3 sensors, and this is the reference crucible. So it should be made up of the same material. So we have currently aluminum crucible, so this is also the aluminum for the reference, and this entire accessory is the furnace. So it can go up to the temperature actually 800 degrees Celsius. Now we have to mount the sample here. So this you can see, this is our sample which we have prepared. Now this one need to be mounted here carefully, so that it should be inside the 3 sensors carefully, and don't press it hard, otherwise this sensor will break down. So now you can see it is completely horizontal, and you have mounted it carefully. After that, do not forget to cover it. So while covering it, this covering will make sure that you are maintaining an entire covered chambers. And now for that, just to maintain the temperature of this thing, you have 2 gas arrangement. One is for nitrogen gas, one is for argon gas. And once it is done, so you can just carefully put this cover, outer cover, and after that you can slightly press it down, don't press it hard. So this is in the case that if you want to do the analysis from ambient temperature to 700 degrees Celsius. If you want to go to sub-ambient part, so in that case, that particular place, you remove it, and then you have to connect it to this cryochiller part. So cryochiller here, from here the cooling comes, and for that this will cool the entire furnace. So you can put it on this way, and that will make sure that you are connected to the cryochiller. So this you need to have only that when you need to go for sub-ambient, means lower than 0 degrees Celsius, otherwise you don't need it. Testing for polycaproelectron. So we know the temperature of polycaproelectron is nearly 100 degrees Celsius. So we need only ambient conditions or more than that. So we can cover it here first, and that's all first. So now we have to start the data acquisition software. So for that you have to click on this, and it needs your admin password, so you can give it. And now from here you can see that window what we have here. So on this y-axis you have the sample temperature, and this side you have the heat flow, how much heat you are providing to the sample. Now on this one you have the furnace temperature. So furnace temperature in the red color, heat flow is coming in the blue color actually. So you can come to know what is happening. And the red one is your sample temperature. So you can see that what is happening between the two. And bottom axis is the time. So you can interchange this time with temperature. So if you want to have for temperature here, you can select it maybe furnace temperature, or maybe select it for sample temperature here, or generally people go for time in the beginning, so it looks nice. Now we have to put the experiment part, so we have to click on experiment. Now you say the by default this gives the experiment name and date and time, but we have to assign our own numbers, so we can go for experiment properties, and then we can, this is the sample ID actually, so you can define if you want date and time, keep it like that. If not, you can change according to you. So we want to say that's a polycaprolactone. So you can give that name. So you give the sample name, and after that you have to put the quantity of the sample, how much quantity you have taken. So we have taken there 54.2 milligram. If you can weigh the quantity in gram per mole, you can do that part also, but generally all weighing balance give the mass in milligrams or grams, so you can put that quantity. After that you have the option just to choose what type of aluminum crucibles or crucibles you have. You have 100 microliter, 170, 30 and all those, so you can choose according to that. And we have aluminium. First is alumina actually, so these were alumina one, you have platinum one, you have steel, you have tungsten one, and then you have alumina. So alumina we have 120 microliter, so we can select that one. So this is the sample in the nomenclature part. So once we enter the sample details, that the sample name and quantity and type of aluminum crucibles and its volume, then we have procedure summary here. So you can write a comment that how have you prepared the sample, something. So you can write the summary here. Further, you can write here, these are your safety guidelines. Let's say you want to have a test sample, something, and temperature, carrier gas, whatever you are taking, air, nitrogen or argon. So you can select it from here. And this is the CFT temperature. So for this furnace currently which we have, the maximum temperature can go up to 710. So for safer side, we are not allowed to go more than 600 degrees Celsius. So that temperature we can define from our side. Let's say we want to make it safer side 500. So if we have fixed it 500, so somehow in your heating or cooling zone of the sample, if you give us a temperature of 600 or 510 or 50, it will not go to that one, because you have kept a cap of 500. It will give the warning that something is wrong with the sample analysis. So these are things. So our carrier gas 2 is actually the nitrogen gas we are using, and carrier gas 1 we are not connecting. It is connected to the argon actually, so we are not taking that part also. So we have carrier gas 2 is nitrogenol. So once you have fixed up all these parts, after that you have to go here, you have to put your temperature zones. So means we need a heating zone, cooling zone, standby temperature. So we can put a standard zone here. Now if you see here, you can find this thing here from where the temperature will go, your final temperature, what should be the heating rate and how much should be the time. So if you fix up the time, your heat or let's say heating rate is fixed, time would be calculated automatically. So let's say first part you want to have a temperature currently, let's say you want to have it from room temperature. So if you are not maintaining with some air conditioner or something, in hot climate room temperature you can put maybe 30 degree, maybe 35, or let's say in cold climate you would have a temperature, let's say for 15 degree due to cold weather. So you can put that temperature. It's better to put the temperature which is of atmosphere no need to put a temperature which is not there in the atmosphere, because you will not get the data in that range. Or you turn on the chiller if you want a temperature lower than this or something less than ambient, so turn on the chiller for that. Otherwise, no, you are always expected to have a temperature near to atmosphere only. So let's say the first one we want to go for time being, our room temperature is 30, and we want to put 30 to 30 just to have this 30 to 30 means you want to maintain the sample temperature 30 for, let's say, for a time being of 2 minutes. The purpose of this, it will just make sure that your entire sample, because you have put a sample which have some actually a lumps or a powder, and some may have a temperature outside environment, some will not have it. So if you will give a temperature for some time, it will make the uniformity of the temperature of the entire sample. So you can hold it at maybe for 2 minutes. That is sufficient time. So once you gave it 2 minutes, so you can turn on the valve here. So both the valve is on. So here, if you are not clicking here, it means the carrier gas 1 is on. So 1 is argon, which we are not connected. So we are clicking it here. It means the carrier gas 2 is on here. And we should make sure always the fan should be on, because fan is the only thing which will control your temperature. So first you maintain the temperature of the sample 30 degree. After that you want to have from, let's say, 30 degree, you want to go ahead for, let's say, 200 degrees Celsius. If you don't know the much about the sample, that where would be the glass transition temperature of the sample, so you can give it 200. Now here you have the choice. What should be your heating rate? So let's say you want to have a heating rate of 10 Kelvin per minute. So it will automatically calculate the time. Currently it is in seconds, so you can convert it to the minute. So you can say it is in the 17 minute actually. So it will calculate automatically. Now let's say at 200 degrees Celsius, again you want to maintain some temperature so that entire sample will get the 200 degrees Celsius. So you want to hold it at 200 degrees Celsius. Let's say you want to hold it for 2 minutes. So you can do that part. After that you want to cool down. You want to see that what will happen on cooling. So let's say from 200 you want to cool down for till 30 degrees Celsius. Let's say you want to have the same cooling rates. You can have a different, choice is yours. So you can have a different heating or cooling rates. So currently we are putting a heating and cooling rate is 10 Kelvin per minute, and based on that you can say the total time needed for this system is something so total time would be calculated for here. 34 plus 4 is 38 minutes. So 38 minutes is the time for the sample. So once you have fixed all this property, now you can go to this side is start. You can directly click here. You can start the instrument would start. Or before that, you may go to this menu part here. Go back. So you can see here real-time drawing. How this is how the reference or the data coming from furnace for the time being. It is off actually. You can see here the furnace parameters. These are some PID controller things, so we don't want to interchange or change anything here. Manual program here, so this you can do before in the beginning. You can turn on the gas here. If you want to modify, you can modify here gas, turn on the fan, and now you can see that some noise has come in the DSC. It means you have turned on your fan. So that what will it do? It will take out the excess here from this pipe which are connected, which are giving you the gas supply to your furnace. So sometimes excess pressure build up, so that will be taken care by this fan only. Too much excess pressure maybe disconnect your connections. So once it is done, and now you can see here the security temperature is clearly mentioned here 710. So we have set in the base program means earlier, that is 500 degrees Celsius. So this is the part you have to make sure in the beginning. Now we have here two gas connections here. One is the nitrogen gas, one is the argon gas. So depending on the environment in which you want heating or sample analysis to be done, you can select the gas. So let's say this is for the nitrogen one. So you have to open the valve here first, and with the help of this control valve, you have to set the temperature is 2 psi. So 2 psi is the maximum guidelines fixed by the instrument. So you can fix it up with this help of this valve. So you can close it, open it till it becomes the 2 psi. So slightly up and down would work, but not very higher than that. So once you have set everything, the sample parameters, your heating and cooling zone temperature, is the standby temperature, your heating zone 30 to 200, then the standby again at 200, then 230 degrees Celsius. You have turned on the gas carrier 2 from here, and this is for fan. Everything is on, and then you can see that if you see here, the green signal means your equipment is on, and you can see here you can put your hand here, so that can give a feel that instrument is also on, fan is also on, so nothing will go wrong actually in that way. And after that, you have to just click here the start button, and from here just click on start, and you can find here the signal here. So this is what you are getting here, your sample temperature, and this side is the heat flow. So heat flow is coming in this blue color, 0.5 milliwatt, and this is how the temperature is. 27 is, you can see, the temperature of your sample actually currently here. So you can observe it for time being, and let's see how the response is coming. Now to look the graph better, you can maybe put here 10, so you will see how the things are going on. This is what you can see. This is your set temperature. This is what you want, that for 2 minutes you want at 30 degree. After from 2 minutes you want to increase 10 Kelvin per minute, and you have to go for up to, I think, 17 minutes. So it will keep on continuing till you reach to the 200 degrees Celsius. So that much is not expanded here, so you can do that. And this red line is the line of the sample temperature what you have currently. So red line will propagate as the time will pass on. So that would be your sample temperature. So you will see that your experiment is going on here. You can see how this your sample temperature is going on. Now you can see from here sample temperature has been reached to the 53 degrees Celsius. So in the meantime, in the background, you can do your sample analysis or treatment in beginning, so you can minimize this window, and then you can go for this data processing. So here this would need your. Now from here you can go to this one, open zone files, and you can take your any samples which you have already done. Or let's say we want here, let's say some case of coating here. We have this sample of polymer film, and now you see the graph here. So you can change this axis from sample temperature to time, and now you see here there are no very much sharp peak and all this. So those comes only in case of solid material where there was completely a sharp peak. So let's say you can have zinc one, you can see how the peak are completely a sharp change. Now you see for this side there are no one, there the change from here, but not abruptly. So in that case also you can find your TG just the same procedure. So click on that, on this means temperature profile curve and go for glass transition. Select the point anywhere at two ends here. It will means calculate your glass transition temperature here. So TG is coming something 71 degrees Celsius. So you need not to worry. So if you can keep on changing these points also here and there, this calculation here doesn't change. So if you see here, so either you select this, move the point slightly here and there won't be any change in this TG. So that is the beauty of this particular software. It automatically take care and calculate from the tangent where the sharp change comes. So no matter where the points are, so you can calculate it automatically. Now let's say you want to calculate here enthalpy of fusion here. So you can again click on this one. So and then go for baseline construction. So click on this and then select the 2 point where you have a dip, and this, based on that, you can calculate here this enthalpy of fusion, that is 3.286 joule per gram, and then you have a starting and closing ends here from where this transition taking place and completed, and based on that you will get this particular part. So we can see that at the end of that time period, 38 minutes, you can see that how beautiful graph you got it actually. So first 2 minutes you have standby temperature, which we have maintained something 30 degrees Celsius in the beginning. So this is the temperature line. Red line is the temperature one. So you have the temperature here. And blue line is heat flow. So you can read this axis for there, how much heat the sample is getting absorbed. So therefore all these things are in minus only. Because in the beginning the sample is absorbing heat, so all these values are minus. And in cooling zone, sample is releasing the heat, so therefore things are in plus here. And this you will see there the sharp change here. So this is somewhere in this you have a glass transition temperature there. So we can do the treatment of this particular sample. So if you will go back here, so you can again open the zone file from here and you can locate your sample from here. So this is the sample which we did just now, and this will look like here. So this is in terms of some temperature axis here. So you can say the TG is somewhere here. So this we can read from here. So we can change this thing to time first. So this will look like that. Now if you want to find the TG, so you can click on that, go to your glass transition temperature, and you can select these 2 points where your transition ends. So you will find from here the TG of the sample is 77.08 degrees Celsius. So there would be somewhat differ from your theoretical value, because this is not a theoretical sample, actual sample. Sometimes may have some impurity, maybe some different molecular weights. So TG is a strong function of molecular weights and composition on chain length. So it will vary from sample to sample. So it's better to find your own TG for each sample. And now let's say you want to find the enthalpy of fusion for that. So you can click on this sample again and go for baseline construction here. So you can click here from where the transition is, and from here you will find the enthalpy of fusion here. So this is your CP value. Enthalpy is that one, 73.969 joule per gram. And from here you can find this from where the transition starts and ends. So it started this here 54.43 degrees Celsius. It ends at 98.72 degrees Celsius. And the time consumed during this particular time is 5.6 to 9.9 minutes actually. So it starts at 5.6 minutes and it ends at 9.9 minutes. So based on that you can calculate this enthalpy part also. We did this sample, the previous sample we did here based on 10 Kelvin per minute heating. So if you want to go for slow heating, sometimes you will miss up this transition part, may not be that much sharp. So let's say if you want to put a high heating rate, so let's see what will happen in case of high heating rate. So you have previous sample here which you have loaded property. I want to add something here because once you will do the sample means analysis at very high heating, so you may miss these changes actually. So sometimes you need a very slow heating. Slow heating is most of the time preferred. But somehow if very slow heating and moderate heating are giving you same data, so in that case you have to optimize the equipment performance. So to optimize equipment performance, or let's say better use of facility or power consumption part, so you can optimize the sample heating rate. Maybe 10 people generally preferred, but sometimes if you will miss some transition pass, transition or peaks in the sample at 10, so you have to practically lower down. So it's safer side. If your sample is completely unknown, you don't know any history about the sample, what is being prepared. So it's better to go slow heating as much as possible. So some equipment or DSC analyzers are giving the capability that you can heat up to 0.01 Kelvin per minute also. So that would be a completely unknown sample. You don't want to miss anything into that. So we also want to see, show to you people here that what will happen if you will change that this heating rate, because the relaxation process in the sample would control by your heating rate. If heating rate is very fast, you will miss up some of the transitions, and in case of very slow, you will get it everything. Only thing, it will consume more power and your facilities actually. So let's see what will happen in case of high heating part here. Here all properties are there, sample is here, crucible is here, your zone temperature, everything is fine. Only thing you want to change here the heating rate from 10 to you want to make it 20 Kelvin per minute, and let's see what will happen in that case. So for that you need not to do anything, you have everything. You can clone the experiment from here. So this is now cloned one. You can change the name here, sample property here, this is a copy of the previous one. So this you want caprolactam here, only thing you want here, the heating is now double of previous one. So you can say that 20 Kelvin heating here, Kelvin per minute. So that is the new heating, 20 Kelvin. Rest of the things are same, so you are not doing anything here. Only thing on this heating rate, let's say you want to make it 20, so you can make it 20 here, and same thing you want to for cooling part, you can make it 20 cooling here. Rest of the part is same. So let's say what will happen in case of very fast heating, and that we can practically observe here now. So we can run the sample again and let's see. You can see that graph in that case, there the fastest change, you can see the TG. So TG has come from here, so you can change the axis here from time to temperature. So you can see that this is the somewhere here again, something 57 something. And now if you will see the graph side, so this part your heating zone, and you are heating it up to 200 something. And after that there's the cooling part here. So cooling part in this particular software shows to the upside here. So from here the cooling starts. So this is the cooling curve here. So it will keep on going here, and you will find another sharp peak here. So that will give you and help you of crystallization part, a crystallization zone. So this analysis of the same sample we did for high heating rate at 20 Kelvin per minute. So you see in this case this peak is slight sharp here because time taken is very short. So now one thing to note in this graph that you might have seen earlier graph here that this line was completely horizontal, something like that. After that, it was going down, right? So if you want to, this is because you are the heat flow curve. So you see here, this heat flow curve in this zone is slightly going upside. So this is due to that you have not cooled the temperature, means the sample to your furnace temperature somewhere 30. It has not come to the 30 degrees. So you have to give some standby temperature of the sample so that your this sample should bring down to exactly 30 degrees. So you have to run for, let's say, 5 minutes or 10-minute time if you are doing reheating immediately after the first heating. So this part should be controlled by you people. It's not, you cannot trust completely on equipment that you gave it cooling to up to 30 and immediately you are making it to 30 to another cycle. No, it won't work that way. So for that part, you give the standby. In the previously we were giving 30 to 32-minute time, but after first cycle, you have to give it probably for 10-minute standby time, so that your sample should bring down exactly, at least entire sample should bring down. Because you see here the temperature is fine. After that is going up, the heat flow part. It means that the bottom of the sample which is in contact of the alumina pan is at 30 degree, but your bulk of the sample which is inside is not at 30 degree. So to make sure that everything has come to a uniform temperature after first heating, give the sufficient time in that way to overcome this type of problem actually.
This one is here as compared to the previous one. You can see this is the previous graph here, and this is the new graph here. So you can see the change is a bit faster, and you can see that okay, TG is here. So we can do the analysis of the same thing again. So this same sample we did at high heating rate, 20 Kelvin per minute, and you see this particular change is very sharp now as compared to the previous one. So you see the previous one here, that peak is very broad here. Now it is very narrow, so you can see the sharp change. So you can have a further high heating rate, and the high heating rate can give you the sharp change faster. Slow heating rate will make this peak broader and broader, and as far as that TG value is concerned, I hope there won't be much change. So if you will open that sample file, so this is now for 20 Kelvin per minute one, and so in that way, if you will see from here, you see that this is the sharper one here. Now you want.
So practically in this figure, you cannot see any TG here. It's just the melting of the actually the material. TG means practically a sharp change. Means if you will just make this figure the reverse side, something like that. So this is the sample temperature. This is gaining, and after that, there's the immediate dip in the CP value. So here you can say in this part it would be a TG if this is your starting part of the curve. But you say in this case, this is the behavior of this heating means the heat value of the sample. So you cannot find any TG in this particular zone. Only just you have some sort of heating which can be say as melting only. Am I audible? Because I can't find the response from any side.
Yes, sir, you are audible.
Okay, fine.
Find TG, so you can select the TG from here, and you can choose maybe the point here and maybe at this end. This place.
So in this case, we just want to mention there because the software given a tool that you can find the TG by clicking at 2 points, but it doesn't mean that you can click it anywhere, right? So you should know where it needs to be clicked. So it is the transition part here. So if the, let's say this was your heating curve. So if you want TG, you have to put where the transition just starting from here. It is the dipping like that. And after that is getting end. So end would be something like that, and then it will go up actually, go something constant type of thing. Then it's called the end of that. Means completely a S-shaped type of thing. So there you will find the TG only.
You see there are no change in TG here. This is TG. Here is coming this 56.14, and for the previous one here, for this sample here, this was the TG again. Now the TG, you see that its value is coming.
So here in this sample, you can find the TG actually somewhere in this particular zone here. That if it has, because you see from here, this is the constant temperature line or constant heat flow line. After that, it is changed, a sharp change here, and then it's going nearly a constant for in this particular zone. So here you can select the TG point. One is here, one is at this side, and then you can find the half of CP change that would be mentioned at the TG of the sample.
77 something. So you see that your heating rate would also matters. That same sample we want to do it again a very high heating rate, 30 Kelvin per minute, and let's see how the result will come for that case. So let's see for that. So it would be a very fast one. So here we did at further at high means heating rate at 30 Kelvin per minute, and you see the graph, you cannot find any change. So actually because the heating rate is too much fast and you have missed up that particular zone where transition would occur, because that's the reason for here. So it is always means advisable just to go for a reasonable heating rate, or you can say practically a slow heating rate, that is 10 Kelvin per minute something. So that is the point here, because here you will see there are no sharp change there where you can identify this part is the transition zone something. So if you go to the processing part again, and if you can open this particular file, so you will come to here. So there's nothing here. Here you have a sample temperature there, and you will not find anything here. So you would totally confused that what wrong with your sample. But there's nothing wrong with your sample. Only thing you are not giving is time. There's something it's called the relaxation time and experiment time. If your experiment time is such a fast that it is overcoming your relaxation time of the sample, then you will not find any change actually. So it means your experiment time should be such that it should be something is in between or close to the relaxation time or lower than that. Only then you can find a change or glass transition part. Otherwise you won't be, because you will find a continuous heating, something like that. You will see here is gaining the energy and there's something like that, and there's again gaining. So here you are heating in the beginning, and here you have some change here. After that is here some change, and then it is decreasing and decreasing. After that is gaining some energy further. So if you will find let's say TG for this sample here, just like means normal exercise here, if you can say this one, and if this one is your change, so you can say the TG 137, which is not possible, is impossible, because you are not doing something correct. So this end maybe somewhere here part. So here it could be slightly reasonable, but you are not be sure about this point, because here it's not ending of the session, so it's further keep on going and going. So you are not advised to a excessively high heating rate, and therefore you 10 heating rate is always advisable, or moderate heating rate. It will give everything fine and no sample relaxation. And as a general rule, you can find 10 is good one. Otherwise, you can go for 20 if you want a faster change, but still you see the nature of the curve here had distorted a lot compared to here. Here you find a change, here a change, here then decrease, the change occurs, transition occurs and ends. So this is good thing. This graph would be much more better if you can provide a heating rate further lower, maybe a 5, maybe 1. Then you will find a straight line here and there's a perfect graph here. So that need to be taken care of while fixing the heating rate.
So this was something that how to collect the experiment, actually do the experiment part. Actually, so far we have talked about how to do the analysis part, demonstration, some heat flow. And I hope many of the participants will already know that what is DSC analysis is. But still, I will explain it quickly, actually, so that you can see that in brief what DSC analysis collect and everything. So first part is the calorimetry part. What calorimetry means is, calorimetry is a measure of change of heat process with respect to sample temperature, so that you can measure with respect to time and temperature both, and then limit the environment, how your sample is behaving whenever there is a temperature change, right? So temperature change could be by atmosphere, or we can change it from our side by manually man-made part of thing. Then these are some temperatures measurement techniques. So I don't want to discuss means, because you just need some thermocouples there. And what you do in DSC, you just want to measure the property, something with respect to change in temperature here. Then the thermocouple part, and in case of the DSC, practically you have two base material, the reference material. So this is how your connections are there in case of DSC. And then when you melt a pure material, just like a metal something, so this is how your melting point and temperature will come, because that means initially you are providing a heat of temperature. So initially entire sample would be a uniform temperature. Once this gain the temperature, then it will gain here, it will reach to a temperature to a melting point. After that, it will get completely melted there. So this is the starting of the melting point. After during the melting or phase change, temperature doesn't change. So therefore you have here a constant temperatures are line. After that, it will further go up. So this zone is called a melting zone. Now you see from here to here, there's the sharp change here. You see from here, there's the sharp change here. There's a sharp dip here, CP value, then it's constant. So in between of these two transition part here, there would be a the transition that's called, in case of polymer, it's called a glass transition temperature here. There's the sharp change in the CP values of the sample. So what DSC measures actually, practically is measure the difference between the heat flows into the sample and the reference material there. So that's what is collect. Now this is what you have in terms of milliwatt and millirate here, and then this is something of features of equipment you have. So this equipment what we have from Sateram, France, can go up to this -70 to 200 if you are taking through the chiller mode, means that from sub-ambient to ambient condition, you cannot go here for the 700 or 500 because you are connected to the chiller. So chiller can maintain up to the temperature of 200 only, from -70 to 200. So if your gas medium is changed, you have air, argon, or the hydrogen, then then in case of that, you can go to the -50 to 700. So your carrier gas also matters, that how much temperature can be maintained. Now, what these are something thermal analysis. What do you measure in terms of thermal analysis? One, in some of the case, you just measure the rate of change of mass with respect to temperature, something that is called the TGA, thermogravimetric analysis. Other one is the temperature. There you just measure the temperature, so that's called is only TTA, differential thermal analysis only. In case of the DSC, you measure the heat flow into the sample, how much heat is flowing into the sample with respect to time and temperature. So time and temperature are your independent variable, and heat flow is the dependent variable for that. And all these are being used just to measure these things: phase change, absorption, dehydration, decomposition, catalysis, kinetics, curing also. These are being done, all these DSC and TG. Then you have calorimetry. You also measure the heat here. Then you need reaction, adsorption, mixing, formation, thermodynamic change. Then you have TMA, thermal mechanical analyzer. There you want to measure the how much is change in the length or volume, just to write the volumetric or linear expansion of metal or material, especially for mechanical purpose. Now, once you calculated all these things, that phase change, transition, effect of additive, finally you are doing all this just to characterize the material and means optimize the process, that what process can give you the best material with best melting point, fusing point, glass transition temperature, stability, so and purity also, right? So that can also be characterized with the help of the DSC analysis or thermal analysis of the sample. So this is what the thermal analysis covers: temperature and a property. And property could be your CP value there. So these are various properties which are generally measured: heat flow, weight, length, modulus means your length, volumetric and linear expansion part, and viscosity. So you just do in case of the rheometer also. So rheometer measures the viscosity change of the sample. Now this is the typical DSC curve. We have seen our thing. So in the our sample of this polycaprolate, the electron, everything was not present. But here everything is being present. What is you generally can expect in a DSC analysis. First part is this: the uniform temperature of the sample. After that, suddenly there is a sharp dip, and this is called your glass transition temperature. So glass transition, the definition is that a material will behave just like a solid below that, and it will become the rubbery or soft by the touching by hand a higher temperature of that. So that's called the glass transition. So glass transition should not be confused with the melting point and all this. Melting point means when everything melts. It's not that way. It just changes its phase from solid to rubbery state. That's called glass transition, practically for polymeric samples. So from here, there's the CP here, then you draw the tangent part at this particular part here, and then so there would be CP, some TG value somewhere in mean of this. After that, once your TG has been done, then it will go to the melting point. So you will have your sample will keep on gaining the heat. It will get a uniform temperature further, then it will melt completely. Once it is melted completely, then your transition part is over in case of heating zone. Now you can follow just like here, then you have the melting here. So means first you have a glass transition followed by the melting there, because it will further decrease the temperature of the sample reaches to the melting point here. So it will reach here, then this zone is called the melting. So for this the transition and melting completes the heating zone. After that, you have a cooling zone part. So cooling zone part need a crystallization. You are cooling it. Now the melted material is now getting crystallized to form the crystal again. So that will happen in case of the crystallization form. You are taking out heat of the sample and you will get this type of the peak only. Then you are putting a curing part, you are giving a heat of the sample just like a polymer. It may go to the cross-linking part there, a cross-linker. So you will get a curing process here. So you can cure at a high temperature or low temperature in order to what should be your crystallinity of the sample. Then you can further heat it up. So the sample can either decompose or oxidize. So if your oxidizing environment is oxygen, but you are putting a environment there, the nitrogen gas there. So in that way, the sample will not be oxidized, but your temperature is increasing. So in that case, your sample would decompose. It may decompose with some other components. So that can happen at the high temperature. So if your target is just to test your sample only for TG thing, don't go for excessive heating. So that depending on the behavior or property you need from the sample, just reach the heating zone till that particular point. Don't directly go beyond, let's say directly I will go to 400 degrees Celsius. No, what will happen is means everything will melt, get converted into the vapor, and it will spill out on your furnace. You are going to damage your actually equipment. So that should be taken care. Now, this is what our equipment is. You might have seen already that where we have put the reference and the sample here. And we don't want to discuss much about here, how does it work something. Now, these are the various type of the crucibles which you need. This one is the low pressure one. They cannot sustain very high pressure here. Here you just pour the material, put this lid on top of that, just to make sure that it will not spill or vapor should get control. If you have very high pressure one, then you have to use the high pressure crucibles that can be up to 30 microliter in volume. So these are the high pressure crucibles. Let's say you want to testing of the propellant or the rocket fuel, where practically you need a very high pressure. So this can go to up to a pressure of 500 bars. So these high pressure crucibles need to be used in case of those only. Now these curve we have already seen actually. So first is you have an endothermic part there where the sample is absorbing the heat. And then you have a glass transition also in this part. You will say the glass transition here in this particular zone. Here the change here in CP value. So mean of the CP value change, it will give you the term as the glass transition. Then you will have the melting also, evaporation also. All of them would be in heating zone. Then this is the exothermic part. You are cooling the sample. So you are taking out heat from the sample. So this would be completely your heat flow value would be in positive part only. So what will happen in this case? You would have the crystallization. You would have the curing also there. You would have oxidization in this particular process only. Now this is how your DSC flow comes. So you measure the change of enthalpy change of the sample given CP into rate of change of temperature. And this is a function of kinetics of the sample, right? So there would be due to a kinetic change inside the sample. So total of that would be measure of your DSC signal. Now, conventional DSC means assume that your pen and calorimeter capacities are ignored because you have considered both are of same material. And even if you know the same materials are there, they may not have the same capacity value. But in conventional DSC, they are being assumed that way because that change is not would be 0.01% something. So in that way, those are not being considered. Now, this is how your heat flow curve is coming. This is the heat capacity by heat flow. This is due to by kinetic change. So in standard DSC, all of these comes in cloud factor. All of these are coming as a single heat. You cannot differentiate them. But there are some modulated the DSC. You can separate out them that how much is change due to heat flow, how much is change due to the kinetics of the sample only. So kinetics of the sample part is this part here. This is the due to the change of heat flow only. This is the TG part here. Now, most of the time, all students, all the researchers, everybody in case of DSC analysis are interested in what is the crystallinity, means how much I have a regular pattern arranged crystals inside my sample, how much is amorphous part. So this is how you can calculate the crystallinity part. You can calculate enthalpy of fusion of the sample. So enthalpy of fusion would be this amount only, the total by doing the base heat integration of that. Calculate heat flow and temperature curve area under the peak. And this can be calculated either by the equipment software provided, or they are provided your TXT format of data, or Excel format, just plot it in the Excel, means origin software. You can integrate the peak, you can get the area under the peak. Is that fine? Are you people aware of the origin software? Any participant? Is any participant aware of Miss Origin software?
Yes, sir. They are saying yes. Dr. Gurpinder and Dr. JC both are saying.
So in that case, actually, you can find it area under the curve. Practically, that is the total heat absorbed by the sample, actually. So that can be calculated by the origin software. So you can calculate from there the enthalpy, because the area under the curve will give you the heat flow. You know the quantity, how much quantity of the sample you have taken in the aluminum crucibles. And based on that, you can calculate this value from there. And from our video also, we have seen we have directly integrated the base integrated. You got the enthalpy of the sample. Then you should have the standard enthalpy of the 100% crystalline sample of that you will find in polymer handbook book or some of the reference material. Substitute that here, and this will give you the percentage crystallinity of your sample. Whether it is 100% amorphous or 100% crystal or 30%, 40%, that will come from here. So this is one way to calculate from heat of fusion or heat of melting of the sample. Same thing can be calculated also from heat of crystallization of the sample, also from the cooling zone part also. There you just need the how much is the means enthalpy of crystallization here. So this zone would, this particular peak would give you the enthalpy of the crystallization. Now, when you are there in either calculating enthalpy of crystallization or enthalpy of fusion, then you have to integrate all peak, not only the broader peak or a sharper peak. No, each and every peak which have the, and this is the endo train, every peak must be integrated and total, you must total all of them. That would be the total heat absorbed by your solution, I mean the sample only. And then you will calculate your crystallinity part. Fine. And once you did crystallinity part, then I want to quickly tell you, actually, I don't have much time. I have to cover something else also. So there is something is called potential application of DSC analysis. So you can do in each and every segment, I would say practically, food, life science, process safety, organic and polymers, inorganic materials, and energy. Let's see what applications can be done in those fields. In food case, you want here melting, oxidation, solid fat index, crystallization, emulsion crystallizations. Melting practically you need when you eat the chocolate something. So you want a chocolate. It should remain hard when you are outside of your body or in your contact. As soon as you put it inside your mouth, it should melt immediately, right? So you should have very low value of TG so that as soon as you will put on your tongue, it should get changed into the solid phase to the rubbery phase only. So that is the part. So you will see the what can be done here. So you can see the melting of the sugars here. So there are the various type of the sugars, sorbitol, maltose, and this glucose and the saccharose. So you can do with the help of DSC there. Then you can do the melting of chocolates. So you, nobody like the chocolate which you will keep on crushing by your teeth something. So depend what type of you need actually. Sometimes you want to crush it, so you want a high TG or high melting chocolate. Sometimes you want low, just you just put inside the mouth and just just finish it up. So depending on type of product you need, you have to control it. Then food is fish oil oxidation there. So you can have the omega-3 fatty so you want oxidation here, that at what temperature my food oil or fish oil is getting oxidized. Because if you will, as you say, the people don't make it oil very hot, otherwise your taste and everything would vanish. And it's only because of that, because the content of the food material is getting oxidized or getting changed. So you are practically eating some other material which are not supposed to eat. Then solid fat index. So you can calculate for by this also. So you can see the TG part is from here, where there's sharp change in CP values only. So you will say the TG is somewhere here. Then again for the solid for fat index for chocolate again. Then you have the crystallization part, at what temperature my things would be crystallized, because sometimes you want your product should be sold to a very cold climate, sometime to the hot climate. So if you see, let's say you are making a food or chocolate, which will not remain solid in Indian climate. So nobody is going to buy that, because the Indian climate temperature is actually most of the time 35 or 30 degrees Celsius, most of the time of a year. So if your TG is coming something 35 or something, your chocolate will be always in soft manner. Nobody is going to buy such type of chocolate. So you want to have means its crystallization temperature should be something higher than 35 or something, so that it will remain in the crystal form as a normal conditions. Then in case of the life science part, you can say the polymorphous, purity, solid phase, crystallization. So let's see what you have here. You have polymorphous here, that how this melting would happen here. It means the stability. Then a crystallization part here. After that, you want to say that decomposition is the rate kinetic depend. If you are providing a high heating rate, you would get some other product. If you are doing at a low heating rate, you will get some other different product. So your heating rate will control the decomposition of the sample actually. Okay, so then you will say at the slow heating rate, you are getting entire change of your inside your the sample. So you are getting here practically one change. This is your the TG change, then followed by the melting. And this is maybe a subsequent melting of some material. You see the previous one, just you are getting one change here. So in case of fast heating, you see here, in case of fast heating, you have missed up all two transitions. You have just have only melting part here. So that need to be taken care while deciding your heating and cooling rate. So same thing. Here actually we are going fast. I think you can understand it. Then purity. So you can find that what should be the purity of that. So pure material have a glass transition of something, and after that you are putting some impurity, and then you will say your TG value which keep on the shifting actually. So you can calculate what should be the percentage purity in that way. Then again, you can calculate purity from the melting point. So pure have some the fixed the melting temperature. Impure one will melt it at slightly at lower side. So again, a solid fat index in pharmaceuticals, and then you will have in some applications in terms of cosmetics, just to find silica content in your talcum powder something. So you can calculate that. Then this is for the process safety, that in the rocket fuel something, that you can calculate at what pressure and heat your propellant will work well. So that can also be calculated with the help of the DSC only. This is again, you have here the decomposition part. So you want to calculate at what temperature will your fuel would decompose. So your furnace temperature where your fuel is getting burned, it should not go beyond that. Otherwise your fuel will decompose actually. Then again, this one, the decomposition study, then the thermokinetics also. So you can, and in case of polymering the material, you need oxidation, crystallinity, glass transition, temperature, curing, and melting. So this we have already explained here. So practically TG is the something like that. Here is the sample temperature. After that, the change, and then it goes. So practically, you will select one point here where the change ends. Other points here, from there the change starts. Somewhere in between of these two would be your TG value. Now you see the second TG. So there would be a always change in your TG value when you are the heating it first time and when you are heating it the second time. So first time means your the sample would have some effect on your molding of the sample. What the molding process has been followed something. Due to that effect, your TG would be different. After the second heating, your molding and processing effect would vanish completely, and that would be TG of purely of your sample, which is being used to process that particular mold or object. So second TG would be your the TG of the material. First TG would be TG of the material plus process involved. Okay. And this is the residual curve due to improper curing of the sample something. This can only happen in case of first heating only. Second heating, you see everything is vanished now. Is that fine? Then you have oxidation part here. So we can do that part here. Then you can calculate crystallinity part. I already explained to you how to calculate the crystallinity part. You have the TG here, the sharp change. So integrate both the peaks. One is this peak also, this peak, calculate the total heat of the sample absorbed divided by the enthalpy of the fusion of 100% crystalline sample will give you the crystallinity part. Then glass transition, I hope I have explained already actually. So we have something polystyrene value of the TG. So here the CP change, CP is this, then the further change. Draw a line here, draw a line here, then draw a tangent here. Mid of that would be the TG value. So we can see here the same, the different polymer, the material have different values of TG here. And this is how you will say that TG part that you can say here, the line here, line of change of first thing, second where the transition ends. And then there the tangent here at this point. So this point would be your TG of the sample. Is that fine? I hope for everyone. So we can skip this part here. I want to go for confocal part now. Then you have the crystallization part here. So this way, this is the endothermic part, exothermic, sorry. Then you have melting of alloy here. So pure the material will melt at the one temperature, and they will have only one melting peak. In case of a combinations of the mixture of the material and alloy, you will have two melting peaks. One is here, another one here. So that way you can quantify that how much materials are being present in your actually the sample, and based on this total amount of heat absorbed, you can calculate their percentage also, how much percentage are present in that material actually. So you can integrate both the peaks. So you can calculate the enthalpy absorbed in this peak also, enthalpy in first peak. Ratio of the two will give you the percentage, that how much of each percentage are present. So that can also be used your phase diagram of the system. Okay, so then you have quartz actually in torque. So you can calculate how much the percentage of the quartz, and you cannot go beyond a percentage. And then you have melting point and phase change of other materials. So you can calculate here. So this is the boiling point part here. So melting and boiling. This we can leave it here. So is that fine? Everything for DSC so far, whatever I have explained to you people? Hello?
Yes, so I guess it is okay because everybody, none of them is responding. There are some of the questions from the participant sites.
Okay, so can I answer those here now, or shall I just give this intro of this confocal, because we have already 4. So if you will permit some time, I can explain this confocal, the Raman is spectroscopy.
Okay, just a moment, sir.
Can I go ahead with this depth profile, or shall I answer first the questions?
Yes, sir, please kindly proceed and you
Yes,
can read this topic.
Yes, ma'am. So one part is this depth profiling using confocal, the Raman spectroscopy. So Raman, I think everybody knows the Sir C.V. Raman invented the Raman scattering in 1928, and he got the Nobel Prize for that in 1930. So he studied that what will happen when you are focusing the light or monochromatic beam on a sample. How does it behave with that light actually? And the scattering part, he observed that different material scattered the light of different wavelength, and that is being characterized as the Raman signal. And it is being used as to quantify the sample purity and means to find structures also. For that part, so what happens in the Raman means the spectroscopy I can explain with the help of figure. So let's skip this part also. So let's say here. So let's say this is your ground state of the sample. And when you are focusing a laser beam or light on the sample, what will happen? The sample molecule will reach to a excited state part that is called virtual energy state. And one transition could be that it reaches to a particular state and then it falls back to the original state. So what will happen here? The light emitted by the electron due to this change from virtual to the ground state part is the same frequency, whatever frequency you are putting. So in that case, you cannot absorb any change because same light has been come out, same light has been imparted. So you cannot observe the change. So that is called elastic collision, means change, and that's called scattering elastic one. There is no change in that. There's something is called inelastic change in the sample. You have imparted some light and it has reached to a state which is other than some other ground state. So in that case, the light means the energy emitted by the electron is slightly lower than what you have injected into the sample. So this you can find as a change. So this is called a Raman actually. This called Stokes Raman when the energy of the photon emitted is less than the energy means focused on the sample. Second one is that from here, this was on a ground state, slightly on a virtual state. You have provided further energy to that, and it has emitted a energy more than the supplied by you, and that's called anti-Stokes, means the Raman line here. So these two signals are the Raman signals, anti-Stokes and the Stokes one, and those are quantified by finding a change of different color wavelengths, which you can quantify here. So the Raman means spectroscopy capture these two change, anti-Stokes and Stokes one. Is that fine? So you can see here this graph here. So here this first one is actually the Rayleigh scattering where no change in energy. This is anti-Stokes. And this is the Stokes one. So anti-Stokes and the Stokes line being collected by your Raman spectra. So this is, I already explained to you that how will it go. And this is again the various energy labels J and Q. Quantification based on the virtual state you were present and virtual state you are coming. And based on that, you can qualify their Q branch and J branch and S branch. So since time is not much, so I am going this much faster because then we can skip this one. Now, here that this purity or the rotational, so the Raman sketching can be of two types: stretching, bending, and the rotational part. Based on that, you will get some peak at a particular wave number, and then you have to identify that this belongs to which type of stretching. So I will show you that part also. So before that, we'll see that this is how your confocal, the Raman spectroscope look like. Here, what you have here, there is a platform here, this one. So you have to mount the sample here. So at this particular point, and then this platform can be moved up and down by focusing inside the sample, below the sample, or on top of the sample. And then there's the base or the substrate of the sample you can locate by showing the video mode. So you have a UV camera there. So you can see the video of the substrate that you are focusing on that. You can see the picture. So that's called the microscope part. And then you want to see how the sample behave with respect to light chain. That goes into the category of the spectroscopy part. So you see here, this is how the arrangement look like. So I would explain you with the help of the another picture here. So what you have here, this is actually your platform where you have mounted the sample, your red plane. So practically you are focusing to collect the data only from the red plane. But due to the refractive index change of the material and working depth of this confocal, you will get the spectra from 3 points. One is from the blue plane that is called out of the focus above plane. Below the focus is the green plane, but you are only focusing on the red plane. So to get the data only from red plane, your confocal arrangement helps. So what does the confocal is? From here, the laser beam is coming, and here you have the beam splitter which focus the laser beam on the sample. So laser beam has been passed to the sample with the red signal. Once it comes to the red, it being scattered from a particular depth of the sample. One is top, one is below also, and that is called depth of the resolution of the sample. Now we want to remove those signals, because if those would be collected, we will not get the exact profile of the sample. So in that case, your confocal, there the pinhole here, it is at the focal length of this particular objective only. So whatever the signal which are coming away from the focus of this particular length, that would be cut by this particular pinhole. So you see that blue and green are getting cut here. Blue and green are getting cut here. Only the red signals are passing through the pinhole of the camera. This is called the confocal arrangement. So confocal arrangement is nothing but just to cut the signals from out of focal plane so that you can do the depth analysis of the sample. Now you can see this this actually metallic picture here. So this is my case in case of you have the liquid samples or a polymer sample which you want to dry. So you can pour the sample here, and this complete sample holder can be put on this red plane to locate it to your, hello? Anyone wants to say something? So, so here you can locate it, you can pour the sample, and then you say the red plane, blue plane, which I have explained to you completely. And then you can collect the spectra. And let's see what will come from the spectra actually. So I want to explain you with the help of this polystyrene, paraxylene, and tetrahydrofuran the sample. We have this particular polymer film, and what will happen in that case. So you know that each particular compound have its own signature peaks, and those need to be studied first before you want to make a sample for a confocal. Any sample practically can be analyzed, but most of the time people buy the equipment without spectral separation of the peaks. So wherever the peaks are very close of the two compounds, you cannot identify them, and you will say, okay, my samples are not correct. No, Nothing wrong with your sample. Only thing, your peaks of sample, mean the component 1, component 2 are very close. You cannot identify them. That's all. Due to your constraints. So you see here, this is the spectra, Raman spectra of your this polystyrene. So you see there the several the Raman peaks here, these one. Now you see now the next one is paraxylene. You have the several peaks. Next one is the tetrahydrofuran. These are for pure compound, tetrahydrofuran, palestine. Now you see that peaks, the several peaks are present in each of them. Now you want to quantify the combined solution or the sample of polystyrene, paraxylene, tetrahydrofuran. How would you quantify? Which peak need to be considered? So if you will see here in this particular part, there the peak here is this 910, right? Can you see this? Any the response from anyone?
Yes, sir.
So you can see here there's the peak here at the 910. Now let's see paraxylene. Do you have the peak at 910? Here you have 800, here you have the 900. So you don't have a peak here at 900. So it means paraxylene and tetrahydrofuran can be characterized if you have mixed up both the two. Now let's see the polystyrene. Does it have the peak at the 900? So polystyrene also doesn't have the peak at 900. So it means this system can be studied combined system without much more the difficulty or without a need of peak separation software. So it have a peak at 1000. It have a peak at 826. It have the peak at 900. So these are three characteristics peak which are not present in other samples. Means you have to find the compound such a way that you should have at least one peak which should not be present in other samples in order to quantify them. Just like that, there are the three boys in a particular, let's say, class. All of them face are covered. Only then you can identify with their colors. So you can color means here are the peaks. So if you have the different colors or different peaks, only then you can identify them, right? So once you will do combined spectra of that, I have just taken the spectra which I am considered. Practically you can have it from, let's say, from 50 centimeter inverse to 4000 centimeter inverse. So I don't want to focus in entire zone and unnecessarily base the power of the confocal. I'm just focusing here where my peaks would like of all three samples. Polystyrene we have fixed at 826, tetrahydrofuran 900, polystyrene at 1000. It means these three can be characterized, and these peak assignment, name and treatment, smoothing of curve again can be done with the origin software only. We did another system also, polystyrene tetra. So practically you have, this is the first part. You have to prepare the sample that at least in these peaks, you will have at least a gap of 50 centimeter inverse. Otherwise, these two peaks would get merged. If you have one peak at 827, another compound have the peak at, let's say, 840 something. So there are chances of that the peak may get merged and you will not be in the position to separate them without a peak separation software, right? So that part that can be taken care of. Now, once you did it here, this is what would come from your Raman spectra only, that's all. What can you do here? So they will give you the data in TXT format or in Excel format, intensity versus wave numbers. Now, software always comes with the equipment. You can do complete treatment. You can calculate your peak height also, how much is the peak height, how much is the area of the peak. Everything can be calculated by the software. If they don't do that way, because sometimes people charge it, it takes time. So in that case, you take them TXT format of the data they provide, put it in the origin, just do all these treatment, everything very nice. You can do all things very well there. Okay, so you calculate from here intensity, height of intensities of the peak. Some people say area under the curve also, but for depth dependent concentration profile, I would say just go for height of the peak only. So you can calculate height of peak of polystyrene, 800 tetrahydrofuran and all this. Based on that, this is what you will get from the signal. From the height of the peak, the ratios, you can quantify which one is more, which one is less. You cannot quantify how much percentage, what is the concentration. No, you cannot do that. To do that, you have to prepare standard samples of these two, a combination of two. One is polystyrene, paraxylene, tetrahydrofuran, paraxylene. Those are calibration curve, a standard samples, and then again take these intensities graph. And then you plot this one. So you have prepared a polystyrene tetrahydrofuran samples of different concentrations in the sample bottles. You can do with the confocal, you can put the sample in your quartz bottle, quartz cuvette also, to get the spectra there. So you can do everything with the confocal, powder, liquid, solid, everything. Even if these days there are the something gases also coming. Then you calculate intensity and plot this curve, intensity versus intensity of polymer of the solvent, gram of polymer of the solvent, then you will get a calibration curve. Once the calibration curves are prepared, then you calculate your actually your concentration from here. This is what you have prepared. This is what you have calculated from binary curve from your some known sample, and then you see the difference that it is perfectly matching. It means your calibration curves are fine. So you can calculate concentration that way. Now, once you calculate concentration, you can do the analysis of your sample now. So I did the depth profiling of my polymer film at 50 micron, then 100 micron, then 200, 300, and we validated with some the model. That's not part of the concern. I just want to know that we can collect the depth dependent data from confocal. Then this other people did it here. In case of polystyrene, you can do with the time how the drying will take place or curing will take place. Only thing in the problem with the confocal is you cannot control temperature, you cannot do any heating, you cannot do any cooling. Only thing it is being done in the chamber temperature only. So only thing you can do the evaporative type of drying only. So here you can see that how this concentration is getting changed with the entire sample thickness with respect to different times. And the beauty is that you can calculate exactly at every micron depth. Now this is another thing I did for the dry polymer, the dried for film thickness. You see on the top side here, concentration are very same actually, and bottom side you have a change there. Now this is what you have a handbook of the Raman frequencies. Once you did analysis of the sample, you want to assign this peak comes to which particular compound, which stretching, and what bond, what functional group. So there are complete book here. So I have listed here all of them here. So these would help to assign you or characterize an unknown sample. So these are all the Raman peaks which you will find. And then after that, you will have a depth profiling of, let's say, how your chocolate or any food material or any sample of engineering application, just like your banded something, or you want to have a safety of a container. So you want to find a crack also, how much is crack, how much purity at each and every thickness. So you can do the depth-based analysis here, and by finding a change in intensities of the sample, you can find if the intensity of the sample is changing as each and every depth, it means your composition is not uniform of that particular sample. You can do this horizontal means a plane-wise analysis at a particular plane. What is my concentration change here? So you can say that if you will say focus at this side, this left and right, if your intensities are changing from to moving on a particular horizontal plane, it means your sample is again not uniform. So you can do the horizontal analysis, you can do vertical analysis, and just to find that how much change are there. If your change are allowed, you do it. If not, you have to suppose to change your sample or control your process manufacturing part. So you will see these are again your depth dependent the spectra. If you have, let's say, pure sample, same sample, then every depth you should get only same peak. All these peaks must be overlapped, but these are not overlapping. It means you have a different composition at every depth. 6 micron, 8.5 micron, you have the different composition present. However, you see from here to here, your peak is only same, your compound is only same, only thing is composition is getting changed. This is again the layer by layer characterization. So each layer you will have a different peak, and based on the new peaks arising or peak height, you can quantify your concentration, as I explained you the previously part. This is again the depth profile. Now, what is the important aspect of confocal part? First part is this, as I talked to you, that the sample correction area, that how broad should be area is. In case of the solid, this phi value should be as low as possible, because in case of crystal, your intensity becomes too much high, sometimes 45 lakh something. So your equipment would become saturated in terms of peak height. So you have to minimize this window size. In case of the liquid samples, the peak intensities are very poor, so you can make it broad actually. So in case of the solid sample, you can have this 2 micron hole size. In case of the liquid samples, you can have 40 micron hole size actually. And this is again the Z is called that depth, the resolution part, which we can control. How can we control? I will tell you here. So this one thing is called a working depth of the sample. So let's say you have a sample which is very thick in size, and by chance working depth of the sample is very low. You cannot use those type of objective lens, because the laser beam will not penetrate till that particular height. So you have to change the objective by a long working distance, so that your objective should not touch the sample surface. Otherwise, the objective lens tip would get damaged. So what you have here, let's say this is your objective lens. From there, the laser beam is coming. Now, in between, let's say this block is the sample of the material sample. You want to characterize it. Let's say you want to focus only at this particular point, which is S here. But due to the refractive index change between the material, between lens and the material and the sample itself, so it will have the refraction of the light, and due to which you are getting some light will go to this depth here, other component of the light from here would go to this depth, and this particular gap is called depth, the resolution, which is your delta Z. And this need to be practically minimized, because we want to collect the data from a particular point, not from particular length, right? So you want to minimize it, so you can control it by keeping the refractive index of the material in between of lens and sample nearly same. So if you have a dry sample, people put the metallurgical oil here, there, mineral oil, so that it should have the refractive index same of the sample, so that this thing should not happen, and Z can be minimized. Actually, it can minimize to 0 something. If not, it's not in our hand. So if you say that the refractive index of the material is 1.5, wavelength is also in your find, because the laser beam, the light in your control. So you can have this also, but you cannot have 1 or 2 more options. You can have only 2, 3 options there. So that is also fixed to you. This is also fixed. This is also fixed. Numerical aperture of the lens can be changed, because practically it comes with the lenses 100x, 40x, 20x, 10x. So you can change them. So for 100x lens objective, the numerical apertures come 0.95. If you will, the substitute is delta Z is coming 0.9 micrometers. It means something less than 1 micrometer. So it means this gap is 1 micrometer. So if 1 micrometer gap means the data collection is fine for you, it's okay. So next depth should be 2 micron or 4 micron. If you are just going 1 micron, it means you will not able to quantify it because the depth, the resolution itself is 1 micron. So you have to go for the step size more than depth, the resolution of your system. Is that clear?
Yes, sir.
So that way you can control it. Now this is another thing that how this look like. So sometimes people fill up the water, sometimes people fill the oil, just to make sure that there should not be any refraction of the light. Okay. Now this is some the reference. Before ending that, I just want to show it to you that how this confocal microscope the look like. These are the very short videos. I hope it would give some interest from the participant side. Can I share these?
Yes, sir.
Okay, good.
The sample is the aspirin in powder on a microscope slide. The microscope slide is placed on the motorized stage.
So you see here, this is the platform and there's the glass slide here. So you can put the sample on there. Your sample can be directly put on this glass slide, or you can actually you can do by putting in some metal or something. Choices are yours, so you can do that part.
First step is to visualize the surface of the sample. So I will start LabSpec 6 software and I will select the video mode. For the sample visualization, I will choose 10x objective. Using the joystick and the stage wheel, I will focus on the
two choices. Either you take this stick, you can move the platform left, right, up and down, or you can move it by hand. There are the two knobs here in the bottom side here, this one. So you can move this platform horizontally and you can move it up and down. Hello?
Sample, checking in the same time on the computer screen. As you can see, there are several crystals with different sizes and shapes, and I will select one of them. For the measurement, we will use a long working distance objective, for example 50x objective. Then we will adjust the focus on the sample again. Let's choose the acquisition parameters. First, the excitation wavelength in this case will be 532 nanometers. And the grating will be 600 grating per millimeters. Because the sample is not photo or thermosensitive to the laser, 100% of the entire power of the sample will be used. An acquisition in real time will be launched for 0.5 seconds. This is the Raman spectrum of the aspirin obtained in 0.5 seconds. The Raman bands are narrow and very well resolved. Nevertheless, we note a small fluorescence background. It can be successfully removed by using an option called flat correction. This option, and I will launch again a real-time detection to see the changes. It can be easily observed that the background is almost eliminated. Now we have a very nice baseline. I will stop now the real-time detection and I will launch a Raman spectrum acquisition for 1 second. 2 accumulations will be used for a better signal-to-noise ratio. This is the Raman spectrum of the aspirin easily obtained in one shot, with a good signal-to-noise ratio, as you can see. For the
so you can change here the acquisition time, actually 2 acquisition or 10 acquisition. So in case of big signals of the sample, or let's say very less concentration, you can give it more number of the acquisitions, maybe 10. And so that you should get very sharp peak without any noise. So that would be help in that particular case.
further spectral analysis, we can follow, for example, the band's maximas. But follow us in the next how-to on the spectral analysis, coming soon.
So shall I ask some questions from the
Yes, now we can have the questions actually. I'm just
The question says, what are the advantages and disadvantages in using STA, simultaneous thermal analysis, as compared to standalone DSC and TGA?
actually the thing is that when you will club so many things together, you are compromising the sensitivity actually. So if your target is just to measure the heat flow of the sample, you should go only for DSC part, because it is dedicatively only interested or measuring only the heat flow signals. Okay, so if you are clubbing, let's say DSC with TGA part, you have a weighing balance there, and there you have for DSC you are flowing air on that or gas. So your weighing balance would keep on fluctuating. So your sensitivity, you are compromising the sensitivity of your TGA analysis in that way. At the same time, so that way, if you are taking combined system, you are compromising with the sensitivity. So that depend how much can you compromise. If you are very much dedicated, no, my heat signals should be 100% correct. My weight loss should be 100% correct. Just like the pharmaceutical products, you cannot compromise with the sensitivity, because even if the ppm change of concentration of the drug may be very harmful to the consumer, because direct consumers are humans, right? Humans or the living beings. So in that case, you cannot compromise the sensitivity, because sensitivity compromise means you are compromising with your analysis part. So even things would change in ppm. So that is the only part. If your budget is not allowing, then okay, you can take a combined system, so that for academic purpose you can analyze everything, but you are compromising something for the sensitivity. For the R&D purpose, no, you cannot compromise. You need a standalone. I hope this is fine.
Yes, sir. Sir, now Dr. Jaspreet would like to ask you one question.
Yes,
good afternoon, sir. That was a very informative session, and I think it's a mixture of practical, both practical and theoretical knowledge. Sir, we are facing some problems when we are making the polymer composites.
Okay.
We are mixing metal particles in nylon, normally nylon and ABS we are using. Is it beneficial that we take FTIR, because there is no actually the bonding between polymer and metal, they are just supporting the loads. So will it give any change if we add polymer, if we add metal in polymer and pure polymer, and we are taking FTIR?
Actually, if you will put this FTIR thing, so FTIR, you are characterizing surface functionality of the sample. I hope I am correct. I hope so, right?
Yes,
so, but in case of sample stability or property something, you need is depth analysis part, or let's say how does it behave under the sample, because you are putting a composite. So composite, you want to make it for some application, maybe some in case of fiber, or in some of our fabrication of vessel. So in that case, actually, you just need to go for DSC or this TGA analysis part. FTIR can give your functional analysis, what has been changed within the system, due to which you are correlating now your thermal properties. Getting the point, sir?
Yeah, yes, sir, I got it.
FTIR can only say, okay, these are the new functional peaks or groups has come up now. Before change or after change, then you say the what might mean the property or CP or TG or the melting values before by the impregnant of the material, what is after that. So you can correlate those two, due to which change on means composition peak or the functional group, my functional properties are better.
If in case if we go for FTIR and we are suppose taking nylon and
right,
then we are adding metal particle in nylon. So if we take both FTIR of pure nylon and composite nylon,
right,
will it be a different or will it be the same? Because actually
no, it would be different because see the nylon will have its own functional group, right? So those would always present, but you are imparting something else. Now those may be make the mix up a new transition change inside the material, or that can only be quantified by that FTIR only, that what has come up with that way. Or you can go to the Raman analysis. It can also tell what stretching or vibration peak has been banished now, what new has come, because that you can say there's some temporary bonding maybe happen actually in that way.
Okay, thank you. So one more suggestion we want. We are coating a metal on the polymer surface, metal coating we are trying. And is it beneficial to do DSC testing of the, in that case, polymer and coated by metal layer?
Metal, yeah, I do for that actually. I coat only on the stainless steel substrate, actually, all my films. And when I do DSC analysis, I just peel it out. So if you cannot peel it out, your entire sample is clubbed. So you can cut it out actually.
So means sample preparation will be a challenge in that case.
No, actually, depend. If your entire sample or the final product is metal and polymer combined, because both need to sell combinedly, then it okay. But your target is just only a film only, just peel it off.
Sorry, sir.
If you are coating a film on the metal substrate, right?
Yes, sir.
So in that way, you want to just characterize the property of the film, not the properties of the metal. I hope so. Correct?
We normally do the mechanical testing currently. What we are doing, we
so
just test
mechanical test. Okay.
But additionally, I want to ask that.
So I would say that practically in that way, you cut the entire sample with metal and polymer, because it will help, because you want to coat it just to protect it, maybe for corrosion, maybe from heat transfer purpose. I hope so.
Yes,
and in that case, your temperature of metal, because the metal reach heat transfer rate is faster in that way. So that also would somehow will control your polymer change, which is in contact with the metal itself. So you cut the entire sample. So you can, maybe you can punch it with the help of the die, and sample for this DSC, maximum diameter of the sample is the 6 millimeter actually. So those much can be cut out.
Okay, sir. Thank you. We can try in future.
Yes, sir.
So I think any other participant want to ask the questions? I think Dr. Dean sir, do you want to ask any questions? This question in the chat box, can we measure zeta potential of nanofluid using DSC analysis?
No, zeta potential meter is the different actually. That is by zeta potential, the meter itself or dynamic light scattering part. DSC cannot do, because the DSC don't do any light scattering or the light measurement. It take only heat signals only. So there are no spectroscopy analysis in DSC.
Okay, thank you, sir. It was a very nice and wonderful session. All the participants have enjoyed it very well. So,
yeah, only thing I took the more time. I went very fast because I thought that
yeah,
let's say cover up both the things actually, so that the student or participant can understand. Because most of the time we don't know what can be done. If you know the DSC, let's say only TG can be done. No, it's not. There's several things can be done. Just like confocal, people do the Raman spectroscopy only for imaging, but we also know you can find the depth dependent without any preparation. You don't need any preparation for confocal. It is non-destructive technique also. No preparation, just put the sample there and get the spectra.
Yes, sir. And the best part of the video which you have shown at the starting, the whole procedure of DSC and the sample preparation, all the things. Practically, you have shown us that was a very nice combination in this lecture, because now we are doing this online workshop. So sitting at home, people are just viewing your lab and how you are performing experiments. That is very good experience.
Yeah, you are the right, sir. Actually, taking only PPT throughout the day or 2 hours or something is very not very fruitful in that way. In between, if you can do some live exercise or some video demonstration, so we capture it very fast. Whatever we hear or read it, we capture maybe hardly 5 to 10% of that, and whatever we see, we capture almost 90% or more than that. So that way, video, the demonstration, I find it something good. And yes, moreover, your theme of this was your also Karyasala, so it should be maximum practical side, I hope so.
Yes, exactly.
So DSC I have in my lab only, so I have prepared for that video. Confocal we don't have. Mohali, ISER we have actually. IIT Delhi have, IIT Bombay have, all IITs have. So interested people can contact them for analysis, and for DSC we can do for that.
We hope next year when we are organizing this workshop, it will be offline mode, and we will welcome you here at our campus. And there it will be a very nice experience to listen and practically see all the equipment here. Also, we are having FTIR in our research center. We can organize this workshop same in the future, but in the offline.
Yeah, yes, sir. I would be always happy to join it. Actually.
Okay, sir. Thank you very much. Thanks.
Yeah. So at last, I would say thanks to these organizers actually, the Vice Chancellor Sri Satnam Singh Sandhuji, and Professor Zagvendra, the Vice Chancellor, and Professor B.S. Sohi, Pro-Vice Chancellor, Professor Satbir Singh Sehgal, the Registrar of Chandigarh University, and Professor B. Preslesan, Dean Academic, Professor Sanjeev Singh, Dean Research, Professor Harjot Singh Gill, Associate Director and Coordinator of the program, Dr. Raman Kumar and the Sandeep Singh, and event organizer, Dr. Judge Gurpreet Singh Chauhan, and one coordinator in between in the Gurpreet Singh. So I would thank all of them to give the opportunity to demonstrate what I know, and if something I made wrong, something I always welcome to give the suggestion. So I have shared my YouTube channel there also. You will find some other demonstrations and anything you need from my side. So with this, I will say thank you once again for all participants.
Thanks, sir. Thank you. We will also watch your YouTube channel. It will be a very nice experience to watch the videos. You can share details with us. Okay, dear participants, Thanks for your patience. It was a bit lengthy session, but it was a very fruitful because we have both practical and theoretical aspects in this session.